I'm a geologist, and in particular I study sedimentary rocks with the goal of trying to understand ancient environments. My interests are largely in Earth's early days before animal life inhabited the oceans and the continents. I'm going to talk about, in this talk, geological evidence for extreme climate changes in Earth's ancient history, and specifically focusing on an interval around 700 million years ago when we think that the Earth froze over completely on 2 occasions. And I'll discuss this within the context of other important changes happening in Earth's environment around the same time, including gradual oxygenation of the atmosphere and oceans, and the early evolution and diversification of animals. I will also discuss various tools by which geologists infer ancient climate change from the geological record. I think the biggest challenge for the public in understanding what I do is a matter of scale. We're used to human time scales of tens or hundreds of years, whereas I work on geological time scales of hundreds of thousands or millions or tens of millions of years. And when geologists talk about ancient climate change, they're talking about climate change over these very long time scales. So a common question I hear is whether the current climate change that we're experiencing today is comparable at all to what we think happened in the ancient past. And from my perspective as a geologist, it's just a little blip that's occurring today. It's an important blip because we live for such a short amount of time, but from a geological perspective, it's not much.
It gives me great pleasure this evening to introduce our featured speaker. Tonight's lecture is by Dr. Galen Halverson, and his title is Deep Time Climate Change. It gives me great pleasure to introduce to you Dr. Halverson.
Hello, thank you for coming. It's a pleasure to be here tonight. Now, by way of an outline, what I'm going to do first is give you an overview of Proterozoic Earth history. So the Proterozoic lasted from 2.5 billion years ago to 540 million years ago, more or less. Just about half of Earth's history. I will then move on to discussing how we actually infer paleoclimatology, or changes in climate, from the geological record. Then provide some theoretical basis for why there may have been ancient glaciations. And then really get into the bread and butter of this talk, which is extreme climate changes in the Proterozoic, snowball glaciation. And I guess what I hope you get out of this talk today, it's a good story. I probably won't convince you all of snowball glaciation, but I hope to convince you that it's a compelling interval in Earth history and something really extraordinary happened. And certainly we've convinced a lot of other geologists to get involved. So we'll get started. So one of the big questions that we Proterozoic geologists focus on, and is always in the background of any study of this time period, is the progressive oxygenation of the atmosphere. And we have a decent first-order grasp on what happened. About 2.5 billion years ago, there was a large increase in atmospheric oxygen concentrations. And then they seem to have leveled off for about 1.5 billion years. And then sometime around 700, 600 million years ago, pretty close to the timing of these big snowball glaciations, they went up again. And we have basic geological evidence, and we have understood this for a long time, in the form of detrital minerals and sedimentary rocks that would not be stable under an oxidizing atmosphere. Okay, so uraninite and pyrite in sedimentary rocks indicates to us there was no oxygen at all in the atmosphere prior to 2.5 billion years ago. Following that, we have rocks that are red. These are continental red beds, for example, or soils that indicate that iron wasn't leached out during the weathering of soils. That indicates iron was being oxidized, iron oxides, which is a very stable mineral under oxidizing conditions. So these indicate that there was oxygen in the atmosphere. And it never went back down again to being anoxic again. In terms of the later oxygenation event, this is a bit more poorly understood, but we tend to infer that there must have been another rise in oxygen sometime prior to the Cambrian, when animals evolved, started to swim around, started to eat each other, they had large oxygen requirements. So oxygen must have come up to some level approximating modern levels of oxygen. And now there's increasingly we have geochemical evidence that backs up these geological observations. Perhaps the most spectacular data set I would say that's ever been produced for the Precambrian is this data set of mass-independent fractionation of sulfur isotopes. That's a mouthful. You don't really need to understand exactly what these mean, but just notice how there's this big range in these data right here up until 2.5, 2.4 billion years ago, and then they flatline. That is the signature of oxygen for the first time being present permanently in the atmosphere. At the same time, we have huge perturbations, or shortly after that, huge perturbations in carbon isotope compositions of seawater. Carbon isotopes are a measure, a gauge of biogeochemical cycling. These indicate there was a lot of primary productivity and a lot of organic matter being buried in sedimentary rocks and sequestered into the crust. And then again, we see a similar signature again around the close of the Proterozoic, around the time of these snowball Earth events. We also have evolution of the eukaryotes. We don't know exactly when eukaryotes first evolved, but the oldest convincing eukaryotes date to about 1.7 or 1.6 billion years ago, right in the middle of the Proterozoic. And they then slowly diverged through much of the Proterozoic. Not a lot of obvious evolution preserved in the sedimentary record until we get to the end of the Precambrian. And these are a bunch of different animal lineages. And what we see is sometime around 600, 700 million years ago, the first animals evolved, and then they began to diversify very quickly. Okay, so we have important events in eukaryotic evolution in the Proterozoic. And of course, the evolution of eukaryotes eventually gave rise to major change in just the very nature of the environment, what the primary producers were, what was contributing organic matter to sediments, what was fueling the ecosystems. And we tend to believe that there was a turnover, again, around this time, 600 and 700 million years ago, in the primary producers in the oceans. And then finally, glaciation through Earth's history. We're in a glacial epoch right now. We happen to be in an interglacial, where the northern hemisphere is not glaciated, or not much anyways. But throughout most of Earth's history, we were not in glacial periods, but they're not entirely uncommon. So there were a series of Phanerozoic glaciations, the Endordovian glaciation, for example, the Permo-Carboniferous glaciation, big glaciations, but really the big glaciations in Earth history bracket or bookend the Proterozoic eon. Okay, so these are the Paleoproterozoic glaciations. These are the Neoproterozoic glaciations. These are glaciations we think were global in extent. And it appears, as I've insinuated now, that there is some sort of link between the gradual oxygenation of the environment, oxygenation of the oceans, the evolution of eukaryotes, and finally the evolution of animals and diversification of animals, and these big glacial events. And this is a very active area of research right now, and it's very compelling and motivating a lot of people to work on these sorts of problems. Okay, now we're just going to step back a little bit and discuss how geologists infer glaciation from the geological record, because it's not always very straightforward. So Louis Agassiz is perhaps best well known for first documenting evidence and arguing persuasively for a glacial maximum in the Pleistocene, for extensive northern hemisphere ice sheets. And this was based a lot on work he did in Switzerland, where he saw evidence of the little ice age in the Middle Ages and expanded glaciers, and some of the features they left, moraines, scraped up bedrock, things like that. Louis Agassiz traveled around a lot. When he went to the UK, he saw glacial erratics, big boulders that had been dropped off by the Pleistocene ice sheets over the UK. We have them all over here in Canada as well. And then so he argued, he reasoned that that the northern hemisphere had experienced a very significant ice age. And that's the Pleistocene ice ages. So here is this figure right here shows the coverage of ice during the last glacial maximum about 20,000 years ago. And since then, geologists have done a lot of work on glacial deposits. And back when I was a geology undergraduate student, the story was basically there were 4 or 5 major glacial advances and retreats. And that was based on the geological record. The geological on land, the geological record on land is really highly incomplete, just as the geological record in Earth's history is very incomplete. And in fact, we now know from records of the oxygen isotopes in benthic foraminifera, these are just little critters that live on the seafloor and precipitate out carbonate shells. The oxygen isotope ratios in those shells reflect temperatures and total ice volume on the continents. And these have fluctuated very regularly over the last several million years. And now we know that there were multiple, many more than 4 or 5 glacial advances and retreats, glacial maxima and minima. And not only that, that they were paced by orbital cycles, the Milankovitch cycles, through changes in solar insolation. Now, the recognition of ancient glaciation took a while to set in, but it was already quite a while ago that the first geologists recognized that some glacial deposits probably, or some geological deposits, some sedimentary rocks, probably reflected ancient glaciation. So Hans Reusch was maybe the first that I know of to recognize Precambrian glaciation. He didn't know these were Precambrian glacial deposits at the time, but he certainly recognized that these were ancient glacial deposits, older than the last glacial maximum. So what he saw, this is a nice sketch from his paper down here, he saw these grooves carved into the underlying bedrock. And over the top, this is a quartzite with these nice grooves in it. Then on top of that is a very disorganized boulder clay is what they would have called it. Kind of looks to us like a conglomerate, but in detail it's not a conglomerate. There's a lot of mud in there. It's very jumbled and disorganized. And he then could see that these grooves extended underneath this glacial this diamictite, meaning that this could not be a product of the recent Pleistocene glaciation, and it reflected an older glaciation. Okay, and he got it just right. Here's an example of some modern glacial deposits in Svalbard. Very similar sort of environment to that which we'd envisioned for the previous photograph. This is a terminal moraine to Aldous-Brain Glacier in Svalbard, and it's a muddy, chaotic mess of mud and boulders that have been transported by the glacier from various different locations. And so in theory, if we see a deposit like this in the geological record, it could represent ancient glaciation. The trouble is there are a few other processes that generate rocks that look kind of like this. So if we just see a jumbled mess like that, that alone isn't enough evidence to convince the skeptics that we're looking at glacial rocks. So what else do we look for? Well, here are a couple other examples. This picture in the upper left is one of my favorites. That's a clast in that same moraine I just showed you. This actually happens to be a clast of glacial moraine rocks that are 635 million years old that were picked up by the more recent glacier and scraped. Okay, so the whole face of this clast right here is faceted. The ice sheared off the face. And then it's striated. Okay, so just the glacial scouring, other rocks scouring against that face left behind the nice grooves that we see lining up with the pen right there. Okay, so striated and faceted clasts. Here's an ancient striated clast from a Proterozoic glacial deposit. This is pretty good evidence of ice sheets, for sure. And then a few other types of evidence that we like to see. This right here is called a dropstone. It's a type of ice-rafted debris that's been transported out into the ocean or a lake. It's dropped through the water column as that iceberg melted, and it actually punctures underlying sediments. When we're in the Proterozoic, there is really no mechanism other than an iceberg that can generate a structure like that. Today, trees can do that by, you see trees floating down the rivers with rocks in the roots. Okay? So we couldn't rule out that it was something non-glacial in the more recent geological record, but in the Proterozoic, that had to have been an ice sheet and a glacier, I should say, and an iceberg delivering that debris. And in fact, we have very substantial records of the late Proterozoic glaciation. This is an example from northwest Canada where I've been working. And if you look at that big boulder, these are glacial marine deposits. These are hundreds of meters thick. There's our tents in the background. I think that's my tent right there, if I recall. This boulder right here is the size of a bus. These are really impressive glacial deposits. And they're impressive glacial deposits a lot of places. This is now in northwestern Namibia, where I had the good fortune of working a lot at the beginning of my PhD with Paul Hoffman. And here we see this Chuas formation right up here, 450 meters thick. What it's doing is filling a valley that was carved by an ice sheet, carved out 450 meters of erosion. And then, as that ice sheet retreated, it left behind 450 meters of glacial deposits. And as it turns out, these sorts of glacial deposits are very widespread across the globe. They occur throughout the western United States, several places, or western North America, several places in the eastern United States, up around and Svalbard, Norway, throughout Russia, a lot of places in Africa, in Australia, India, China. They're all over the place. Brazil. In fact, I try to impress upon students what a wonderful opportunity studying these rocks is to get to know the world. I did not know that when I stumbled into studying these as a 23 or 24-year-old. I just happened to have gotten very lucky. But people before me did understand how widespread these glacial deposits were. Two individuals in particular, Sir Douglas Mawson, whom some of you probably know not necessarily as a geologist, but perhaps as an Antarctic explorer. He actually was also a geologist and settled down in Adelaide, where I was before I moved to McGill University. And he studied the Neoproterozoic glacial deposits in South Australia and elsewhere in Australia, and also recognized that these glacial deposits were global. Or at least he thought they were global. In fact, Sir Douglas Mawson was what we call a fixist. He did not believe in continental drift. Now, this was the early days of continental drift, so we can hardly blame him. He died in 1958, really before the hypothesis or the theory had taken root in geology. So Douglas Mawson noticed that there were a bunch of glacial deposits in West Africa, for example, in the tropics. And being a fixist, he assumed that those were deposited in the tropics. So he actually believed in global glaciation 60 or 70 years ago, not million years ago. Shortly after that, Brian Harland presented data to argue in support of global glaciation. This data was paleomagnetic data. I'll talk about paleomagnetic data in a little bit. But he had gotten this data from Svalbard in Greenland, where he spent most of his career working on these Neoproterozoic glacial deposits. And as it turns out, these data are incorrect, but he actually got the story right for sort of the wrong reasons. He also recognized or argued that these Neoproterozoic glacial deposits were very widespread and indicated something very extraordinary happened at this time in Earth's history. Okay, well, we'll just step back a little bit now. In fact, if you look at this figure might be a little bit complicated. It illustrates this idea called the faint young sun paradox. And this faint young sun paradox, really, it was Carl Sagan and another colleague whose name I can't remember offhand, came up with this paradox in the early 1970s. And they knew that over the course of the evolution of the sun, its luminosity increased. So over the course of the history of the sun and the Earth, solar luminosity increased. So it was about 70% of what it is today back at the beginning of the Earth, and it's gradually gone up. So the implication then is under an atmosphere the same as the atmosphere that we have today, or at least 30 or 40 years ago, maybe 30 ppm PCO2 back then if we step back into Earth history, we would have gotten to a point maybe about 202 billion years ago when the average temperature of the surface of the Earth should have been the freezing point of water. Okay? And then all throughout the earlier part of Earth's history, the implication is that the Earth's surface should have been frozen. But of course, Brian Harlan, Sir Douglas Mawson, and all other geologists know that wasn't the case because there's ample evidence for very sort of mundane sorts of environments through much of the Precambrian. This is a photograph of geologist Don Sumner on the 2.6 billion-year-old Campbell Round carbonate platform in South Africa. This is one of but many examples of the sorts of rocks we tend to think of as forming today in the tropics. Okay? And so we know that the ancient Earth wasn't entirely frozen. And the reason for that is of course, CO2. And this is an equation that I often show when I talk about the snowball Earth and give a lecture on the snowball Earth. For a geologist, I think this equation communicates what we need to understand about Earth history, and it explains, or about climate change on geological timescales, and explains the Fate-Young Sun paradox. Okay, so here we've got temperature. This is the average temperature of the surface of the Earth, or the surface of a black body, very simplified Earth, if you will. It's really a function of the solar luminosity. This alpha right here is the albedo, or the average reflectivity of the surface of the Earth. And F is the long wavelength radiation transmission factor. Okay, so that, if you will, is in essence the inverse of the greenhouse effect. Okay, the more greenhouse gases we have in the atmosphere, the more of that long wavelength radiation is trapped to heat up the surface of the Earth. Okay, so both F and alpha are numbers between 0 and 1. The only numbers that can really change in this equation then are S, alpha, F, and T. So if we want to change the average temperatures of the surface of the Earth, those are the parameters that can be tweaked. We don't really have that many parameters. And of course then CO2 is well recognized as being an important greenhouse gas, and along with methane. And so geologists have long understood the importance of the geological carbon cycle in regulating Earth's climate. So this cartoon is a cartoon showing how Earth's geological carbon cycle works. The ultimate source of CO2 is from volcanoes that are tapping metamorphic reactions and the mantle. So they're tapping the deep Earth. CO2 is being emitted at a fairly constant rate to the atmosphere. And this CO2 reacts with water to form a weak acid, carbonic acid, which then very slowly dissolves the silicate minerals on the Earth's surface. And in doing so, it then delivers carbonate, alkalinity, and silica, dissolved silica, to the oceans. And then that carbonate eventually precipitates out as calcium carbonate. So, for example, calcium and magnesium silicates on the continental surfaces are dissolved and replaced by silica and calcium carbonate. And then that calcium carbonate ends up in the oceans. It is subducted in subduction zones and eventually recycled, revolatilized, and that's carbon returns to the atmosphere. Okay, so that's the geological carbon cycle. And the effective time scale of this geological carbon cycle is on the order of 1 million years. And what do I mean by that? Well, this geological time scale, or geological carbon cycle, has what we call, has a feedback entailed in it. It's called the silicate weathering feedback. Okay, so the weathering reactions, which consume CO2 and dissolve calcium and magnesium silicates, for example, are temperature dependent. They're temperature dependent because those reactions proceed quicker at higher temperatures. The kinetics are more favorable for dissolution of those minerals, and also because at warmer temperatures, on average, there's more water, more precipitation. And that also speeds up the rate of those reactions. So when the temperatures are warmer, the silicate weathering reactions occur faster, drawing down CO2. The effect is that cools global climate, and that slows the rate of those reactions. The rate of those reactions slows, and global climate warms. Okay? So it's a negative feedback. And this negative feedback is operated throughout much of Earth's history to keep temperatures more or less at reasonable values, in a reasonable range, allowing life to persist for 3.5, maybe 4 billion years. Nevertheless, we have a whole series of glaciations throughout Earth's history. Okay, so now we're going to go in, as I said, and focus on these late Proterozoic or Neoproterozoic glaciations right here. When I got into this business about 18 or 19 years ago, studying the Neoproterozoic glaciations, there was a lot of excitement, but a lot of controversy over the number of glaciations, the diachronaity versus synchronaity of these glaciations, the severity, the global extent of these glaciations. But in the last 5 or 6 years, we've settled, the geological communities stopped fighting with each other, and we've settled on the likelihood that there are 3 dominant glacial epochs. There's the gas gears glaciation, that's about 580 million years old, and then 2 older glaciations, which we refer to as the cryogenian glaciations, the Marinoan and the Sturdian glaciations. These are actually named after areas in South Australia where Douglas Mawson worked and where I used to work up until about 6 or 7 years ago. These were the big ones. These were the global glaciations. So now I'm showing you the distribution of these glaciations on a couple of paleogeographic maps that correspond to the ages of each of these glaciations. So these are maps showing the distribution of the continents as my co-authors and I think they were at the time these glaciations happened. And what you can see from these maps is that the glaciations are widespread. They occur on many different cratons, continental fragments, almost all of them, for both of the glaciations. And also that they are dominantly in the low latitudes. That's partly a function of the fact that our maps have the continents mostly in the low latitudes, so the glacial deposits on them sort of have to be in the low latitudes. The reason I show you this figure is because we believe that paleogeography exerts a very powerful first-order effect on climate over geological timescales. And at this point in Earth's history, in fact, a major supercontinent known as Rodinia, this is an early reconstruction of Rodinia by my former PhD advisor, who not only was the big snowball guy, but was also the big Rodinia guy a decade before. Okay, so Paul is a big brain. He's really influenced the way we think about Proterozoic Earth history. Anyways, this was his first reconstruction of the supercontinent Rodinia. We tend to put Laurentia in the middle of this supercontinent and all the other cratons around it, Laurentia being North America, as it was in the Proterozoic. This certainly isn't the correct continental reconstruction. There are many, many, many different reconstructions for Rodinia, but most of us would agree that there was some major supercontinent at this time, and by about 750 million years ago, it had started to break up. And just as Pangaea broke up, starting about 250 million years ago. And this would have had an effect on global climate in several different ways, several different effects on global climate. In general, this low-latitude rifting continent would have driven global cooling or cooler global temperatures. One reason is the continents would have been distributed in the tropics, in the low latitudes, which are wetter. So silicate weathering could have proceeded a lot easier than if these continents were dominantly in the higher, cooler latitudes or in the dry subtropics. Okay? And also because these were rifting continents, instead of being a big landmass, they were much closer to sources of moisture. So in general, breaking up a continent is going to drive more silicate weathering, and having that continent or supercontinent in the low latitudes is also going to encourage silicate weathering. Another factor is all these continents are clustered in the low latitudes, where most of the incoming solar radiation is concentrated, or a lot of it anyways. And that would have an effect on planetary albedo. If we contrast northwestern Africa, which doesn't have a lot of vegetation, and might have resembled a little bit the Proterozoic, certainly we will see that the continents are much more reflective than the nice dark blue oceans. So a lot of that incoming solar radiation would have been reflected back out into space. The Earth, on average, should have been cooler. And finally, by the time the supercontinent started to break apart, this supercontinent was already very mature. It had been around for a couple 100 million years. It probably formed about 1 billion years ago, so it was about 250 or 300 million years old. When supercontinents form, they generate very large mountain ranges, like the Himalayas. But then those gradually wear down over time, and the subdued paleogeography, a lot of people think, would have actually affected the silicate weathering feedback. It would have made it weaker. Okay, the exact reasons are a little complicated. We don't need to go into that. But what we can sum up is the fact that this sort of rifting low-latitude supercontinent that we had around 750 million years ago probably had lower PCO2 than other continental configurations. A low-latitude supercontinent would have had more CO2 in the atmosphere, and a mixed latitude continent would have had even more. Okay, so the point is, for a given CO2 flux from the volcanoes, we should have had a lower PCO2, cooler global temperatures at this time. Okay, so now we've got sort of the preconditions for a cool climate in the late Proterozoic. But I'm a geologist, and I want actual evidence of these glacial deposits in the low latitudes. Okay, so these paleogeographic maps look really good, but I'm involved in making them, and so I know how much error is involved and how much imagination is involved in generating these maps. So you shouldn't trust them. And I think they're okay, but they're certainly far from correct. And the implications, as you will see, of having low latitude ice sheets are so big that we need commensurate evidence of low latitude glaciation. So we need firm geological evidence. And that evidence, again, comes from South Australia, it turns out. So in South Australia, there is a very spectacular rock called a tidal rhythmite. This rock right here and right here. This is just a polished section of this rock. So this rhythmite, or this rock type, and here it is right here, in fact. It's so spectacular, I brought a chunk back from Australia, and I even lugged it all the way over here. It's very heavy. From there, it just looks like a siltstone, but it's really an extraordinary rock, and I'll explain why. So as you can see in the picture, there are a bunch of little thin layers, and then there's some thicker layers. Those reflect cyclicity in the strength of the tides. Each one of these layers in there was deposited by a single tidal event. Very unusual circumstances where sediments of this sort can be preserved, but they're preserved in this one place in South Australia, which conveniently happened to be where I taught field school when I was based at the University of Adelaide, which is why I came home with this rock. Okay, this rock has iron minerals in it that when they settled out of the water column into the sediments would have aligned with the Earth's magnetic field. And if this rock was deposited at the low latitudes, then those magnetic minerals should have been pretty flat, just like the needle in a compass would be if you were at the equator. If you were at the poles, they should have been vertical. At the equator, they should have been very flat. Okay? And early measurements of rocks at this age showed that they were flat. But the problem with measuring the angle of these, or the orientation of these magnetic minerals in sedimentary rocks is that they're easily overset by other geological events like mountain building events or hydrothermal events, mineralization events. So you need to demonstrate somehow that these magnetic signatures are primary. And one way of doing that is with what's called a fold test. Okay, if a rock has been folded, if the magnetic signature was acquired prior to folding, then if you unfold that rock, then those magnetic minerals line up in the same orientation. If that magnetic signature was acquired after the folding, then all of the minerals would line up while it was folded. And if you unfold it, then they would unline up. Okay? This special rock not only had those magnetic minerals, was deposited in the ocean, indicating marine conditions, but it was also folded very early. That funny fold you see in the picture is what we call a sedimentary fold. So not long after this rock was deposited, it was folded. Okay, so this gives us the best possible test that these magnetic signatures are primary sedimentary signatures. And sure enough, they are. Okay, so it passed the fold test. And the Alatna These are part of the Alatna Formation, which is a glacial formation. So this rock type itself, although preferentially formed in glacial environments, does not itself indicate glacial deposition, but rocks above and below it do. So we know it was deposited during glaciation. It was deposited right here, very close to the equator, and this means that all the other glacial deposits in Australia that we know are the same age were also deposited in the tropics. Okay, and this is very important. Okay, and I'll explain why. But first I'll point out one other extraordinary thing about this rock. And you can come up here after the lecture and look at it if you like, because you can actually see the layers quite nicely right there. From those layers, geologists have actually determined the length of the day and the number of days in the year, 650 million years ago. So pretty neat rock. A lot of stuff we've learned from that particular rock. Okay, ice sheets reaching tide water, reaching the oceans in the low latitudes. That's important. There are tropical glaciers today, but they're, for a while, not for long, the way things are going, but they're high up in the mountains in Papua New Guinea, in the Andes. They don't get anywhere close to the oceans. For glaciers to get close to the oceans, they need to be part of a big ice sheet. And once we have big continental scale ice sheets at the oceans, that overturns Earth's climate. That takes over Earth's climate because, as we know very well here in Montreal, snow and ice are highly reflective. They're a lot more reflective than the continental surface, and a lot more reflective than seawater, as we can see from this picture. And as a result of the reflectivity of snow and ice, the Earth has three stable climatic states. One of these stable climatic states is an Earth with no ice whatsoever. That's the state that's prevailed through most of Earth history. Very small ice caps are unstable. They're unstable because of the effect of ice. Ice is reflective. If you have a bit of ice, that reflects more incoming solar radiation out to space before it can warm up the surface of the Earth. That makes it colder. That makes more ice. That reflects more incoming solar radiation out to space. That makes more ice. You get the point. Okay, so there's, this time a positive feedback related to the reflectivity of ice. And that prevents small ice sheets from forming and being stable. Medium-sized ice sheets over the poles are stable. And this is the state we're in right now. Okay, we can oscillate maybe between smaller and larger ice sheets, or maybe one to two global or 1 to 2 polar ice sheets. In any case, this is a stable state. Larger ice caps over sort of half of the hemisphere are not stable. And they're not stable, again, for the reason of ice albedo feedback. You imagine once ice reaches some critical latitude in the mid-latitudes, it just takes over the Earth's energy balance. There's a lot of ice. It's making it cold. That makes more ice. And more of that ice is in the tropics where there's a lot of incoming radiation, but that radiation has no chance to warm up the oceans. That makes it colder, makes more ice. It triggers an ice albedo runaway. So if we get ice down to those levels by some mechanism, then very rapidly the Earth will switch into a panglacial or snowball state. Okay, so this is another way of looking at the three stable states. Here we have ice line latitude versus either solar irradiance or log PCO2. Okay, these go back to the energy balance equation. We can adjust either solar irradiance or PCO2 to adjust the temperatures and move us between these different states.
What is PCO2?
Sorry, that's the atmospheric carbon dioxide concentrations. Good question. Yes. Okay, so here is the state we're in today, the interglacial state. Okay, it's stable. And to move out of that state into a panglacial state, we just have to decrease atmospheric carbon dioxide concentrations beyond some critical threshold. And once that happens, the ice albedo feedback kicks in. And over the course of very little time, years or hundreds of years perhaps, then Earth's climate plunges into a panglacial state. Okay, this was understood 50 years ago by very early climate modelers. They realized that there were these three different stable climatic states. They didn't really take this panglacial state very seriously because they assumed that once we were in a panglaciation, there was no way to escape from that panglaciation. Because it's not a matter of simply raising CO2 a little bit to go back to the pre-glacial state. This is a hysteresis, or bifurcation point here. To get back into one of the other climate states requires raising CO2 to extraordinarily high values to overcome the effect of that very powerful ice albedo. And in this particular model, those values of PCO2, atmospheric CO2 concentrations, are 100, 200 millibars. These are very, very, very high CO2 concentrations. Okay. But we have geological evidence, as I suggested, that, sorry, I'm having trouble getting my mouse right here, it suggests that we must have been in this panglacial state because we can't have a stable glaciation otherwise that gives us glacial deposits in the oceans 635 million years ago. But I will add that there's one other hypothesis that has been put forward to try to explain these low-latitude glacial deposits, and this is the high obliquity hypothesis by George Williams. So George Williams reasoned that at sufficiently high angle of tilt of the Earth's spin axis. Okay, so it's the tilt of the Earth's spin axis that gives us seasonality. If we tilt it beyond 54 degrees, then at that point, the temperature gradient on Earth switches such that the poles receive more solar insolation and should on average be warmer than the tropics, than the equator. So George Williams argued that the fact that we see low latitude glacial deposits in the late Proterozoic, in fact, it kind of seems like almost all of them are low latitude, reflected a high obliquity world. And this is not a bad hypothesis. At first blush, it seems to potentially account for these glacial deposits. But it turns out that in detail it doesn't work. And it doesn't work for a lot of reasons, and I won't go into all of those reasons. But one important reason is that the more we tilt the Earth's spin axis, the greater the seasonality is. And a high degree of seasonality is exactly the opposite recipe we need to generate large ice sheets. Okay, high seasonality means cold winters and warmer summers. What we want to generate and expand ice sheets is mild winters and mild summers. So there's really no feasible way to generate big ice sheets with a high obliquity Earth. And there's also no way to increase the obliquity and then decrease it again that we know of, because there's no evidence for a high obliquity at other times in Earth's history. And there are other reasons to argue against it. Suffice it to say, I think we can pretty much throw that hypothesis out. Okay, so we go back to our snowball hypothesis, and what we need to escape from the snowball, and we know we've escaped it because we're all sitting here today, is we need high CO2, extraordinarily high CO2. How do we get such high CO2 levels? Well, the answer is in the fact that volcanoes, indeed all of plate tectonics, are immune to a snowball glaciation. They don't care that the Earth is covered in ice. Their source of energy, of heat, of gases is all in the deep Earth, which is not filling what's happening on the surface of the Earth. So volcanism goes on unabated over the course of a snowball glaciation. And CO2 gradually then builds up in the atmosphere. And we reasoned in the original Snowball Earth paper that the hydrological cycle on Earth effectively shuts down completely so that CO2 can just go up and up and up until it reaches that critical point where it starts to melt low-latitude glaciers. Okay, and we know now that it's a little bit more complicated than that, and that probably we don't need to raise CO2 quite that high. We need to raise it very high, on the order of 100 millibars, which is still extraordinary. But probably to get out of the glaciation, we also get some help from changing planetary albedo. Okay, that goes back to the energy balance equation I showed you earlier. If we begin to decrease the planetary albedo, that decreases the requirement for raising CO2 to really, really, really high levels. And we think the planetary albedo over the evolution of a snowball glaciation gradually decreases, and that's because climate modeling very recently has shown that that the continents gradually dry out, or there are big patches of the continents that become non-glaciated, similar to the McMurdo dry valleys in Antarctica today. And then, of course, those dry valleys then also become a source of dust. And dust blowing over the ice, along with volcanic ash blowing over the ice, is actually going to reduce its albedo, its reflectivity. And that's going to then have the effect of contributing to warming of the atmosphere. So now we have a vision of a snowball Earth cycle. Okay? So we somehow push the Earth beyond this critical threshold and snap into a snowball Earth episode. Once we've snapped into the snowball Earth episode, CO2 must have been low to get us into that snowball Earth episode. And now planetary albedo is very high. So average temperatures are extremely cold, say minus 50 degrees. Over the course of a snowball Earth, many millions to tens of millions of years, CO2 gradually increases, albedo gradually decreases, temperatures warm up until they eventually reach some point where in the tropics, ice begins to melt. And once the ice begins to melt, the ice albedo feedback is going to operate in reverse. We've melted a little bit of ice and snow, albedo decreases some more, that makes it warmer. We melt a bit more ice and snow, decreases albedo, so on and so forth. And very rapidly then, the snowball Earth should snap out of the Earth should snap out of snowball conditions and into a completely non-glacial world. And not only non-glacial, but one now with all of a sudden a whole lot of carbon dioxide in the atmosphere. So there should be a super greenhouse event right after the snowball Earth, right after recovery from the snowball Earth. And then gradually, silicate weathering steps in and does its thing, and CO2 levels decline again. Well, the snowball Earth makes several predictions, okay? And that's sort of the fun part of the snowball Earth hypothesis, is going out and now testing these predictions. And largely Joe Kirschvink, a little geologist with very big ideas, proposed this in a tiny little paper buried away in a big book that not many people have, that there was a snowball Earth in the Proterozoic and that we could test this idea. Okay, so some of the ideas we can test and look for in the geological record are evidence for an abrupt transition from glacial to super greenhouse climate, global deposition of carbonates following glaciation, and that's because there would be all this CO2 in the atmosphere, which would then diffuse into the oceans and trigger weathering on the continents, and the oceans would also warm up. That would all tend to drive carbonate precipitation. There would be a negative carbon isotope anomaly following glaciation, because all that CO2 would have accumulated from the mantle from volcanism, and that has a very distinct low carbon isotope signature. And there might be other geochemical signatures of the very high PCO2 during and after glaciation. So here is a picture from Namibia, and what we see is that the contacts at the top of these glacial deposits are very sharp. We go from glacial deposits with big ice-rafted debris straight into carbonates. These carbonates look like carbonates that would be deposited in the low latitudes in the tropics today. So we go from Antarctica to the Bahamas in the blink of an eye, geologically. And we see these carbonates being deposited immediately afterwards, globally. Very identical carbonates. So here's an example from Svalbard, where I did my thesis research. Again, a very sharp boundary, Antarctica into the Bahamas. Here's the same thing in northwest Canada. You can see it looks exactly the same. Here's one more example from South Australia again, and here's that boundary again. Here these, you can't really see the evidence, but there are glacial rocks below that plaque. Can't seem to get that in there. Oh well. That plaque marks the end of glaciation and the onset of carbonate precipitation. So global and uniform is that surface that geologists have actually defined the base of the oldest geological period yet defined in the time scale based on that contact. So it's an impressive contact. And we see the negative carbon isotope anomalies. Here again is Namibia. We see a negative carbon isotope anomaly that then gradually tapers off towards more normal values around 0 per mil as silicate weathering gradually draws down that CO2 reservoir. Okay, so we see the negative carbon isotope anomaly, we see the carbonates, and we see very unusual geochemical features, including geochemistry that indicates very high PCO2. This is a kind of a complicated proxy. I won't explain it right now. Suffice it to say, it indicates in these barytes an unusual mineral to form on the seafloor that PCO2 had to have been at least 10,000, maybe much higher ppm at the end of this glaciation. And the signature is unique to exactly the end of this glaciation. We only find this really intense signature at exactly 635 million years ago, but it's found all across the globe. And there are a whole series of other unusual sedimentological features, sedimentary structures that we find nowhere else in the geological record. This is sort of contrary to what geologists believe should happen. We've been taught under the philosophy of uniformitarianism, that really we should be able to interpret what's going on in the geologic record based on what we see happening today. But these sorts of sedimentary deposits, like huge seafloor cements, these would have been aragonite fans growing on the seafloor. So if you went walking around on the seafloor, you would have had bloody feet. Sorts of stuff that just doesn't happen today and anywhere else in the geological record. Okay, so we've now gone through most of the snowball cycle, and most of it makes sense. And we're almost done. The one problem, and it's a problem that's nagged me and many geologists for a long time, is how we actually really get into the snowball. How do we snap from high latitude, sort of stable ice sheets into a global glaciation? Why doesn't the silicate weathering feedback that has so effectively regulated climate through most of Earth history, why does that fail us in the late Proterozoic? And the answer was staring at us for a long time in Namibia in the form of continental flood basalts. This is called the Etendeka flood basalt in Namibia. This is related to the opening of the Atlantic Ocean. As supercontinents break apart, massive amounts of basalt, volcanic rock, are extruded and emplaced on the margins of the continents in many different places. We were distracted because there were elephants and lions and giraffes wandering around. And it took many, many years before we appreciated the significance of those basalts. Other people have appreciated that, and it's well understood now that flood basalt volcanism, so this is really the extrusion of massive amounts of flood basalts in very short periods of geological time, are closely associated with many of the major environmental catastrophes in the Phanerozoic, including several of the mass extinction events, the end-Triassic mass extinction, the Permo-Triassic mass extinction, and the Cretaceous tertiary mass extinction when the dinosaurs went extinct, are all associated with flood basalt volcanism. But that association is largely because flood basalt volcanism ejects a lot of gases into the atmosphere. These include sulfate aerosols, which tend to cool climate over short time scales, and CO2, which tends to warm climate over maybe medium time scales. But there's another effect of basalts, and that is that basalts weather a lot more effectively than average continental crust, than granites. They dissolve in carbonic acid in rainwater about 10 times faster than granites do. And so they're much more effective at drawing down CO2 from the atmosphere. So we could see that flood basalt volcanism might result in, yes, a little bit of cooling, and then some heating of the climate in the shorter medium term, but in the long term, we predict that it could generate a cooling event by drawing down CO2. So we look at the 200 million-year-old CAMP event. This stands for Central Atlantic Magmatic Province. This is a vast, vast flood basalt province associated with the opening of the North Atlantic about 200 million years ago, as the supercontinent Pangaea really started to break up. And there was a mass extinction at this time, end-Triassic mass extinction. There are carbon isotope anomalies, and even some people have suggested a mini glaciation about 1 million or 2 million years after this flood basalt was emplaced. I would argue that the flood basalts associated with Rodinia and the breakup of Rodinia were much more extensive, and we have evidence for that. And they were largely centered on northern Canada, it turns out, but also South China and Australia. We probably had several flood basalts about the size of CAMP, all in the low latitudes, where it should be raining and wet, and these should be dissolving very quickly, all contributing to global cooling just at the time of the first cryogenian glaciation, which I think is no coincidence. In fact, I believe it gave us the perfect storm. cryogenian snowball glaciation would have been triggered by a confluence of factors. I already described the effect of having this rifting supercontinent in the low latitudes. Add to that a bunch of easily weatherable continental flood basalts that draw down CO2 through silicate weathering. Turns out that basalts have a lot of phosphorus as well. So that phosphorus fertilizes the ocean, triggers primary productivity and organic carbon burial, further drawing down CO2. And probably the combination of these factors all conspired to overcome the effect of the silicate weathering feedback and initiate snowball glaciation. And in fact, there's data and climate models to support this, but we're pretty much out of time. So I'm just going to skip over this and stop right here for now. I skipped over a lot of details in this talk, and I apologize for that. There's a lot of information to assimilate, but big ideas and fun stuff. And I hope you enjoyed the talk. Thank you.